Okay, is this thing on? Yes. Okay, thank you. Okay, so I just wanted to, some people asked to see some more details on the eigencurve. I called it the eigenvariety here, but I mean the eigencurve associated to overconvergent modular symbols. And so that's what I want to try to talk about now. So the first thing is the goal then is to describe a certain a rigid analytic space together with a map to the weight space with the property that for each point in the weight space, the fiber above that can be put into one-to-one correspondence with certain Hecke eigenvalues, sort of systems of Hecke eigenvalues. And so that, to describe it, so here's what I'm going to do. I'm going to try to describe first the analytic space by telling you what its points are. And then after I've told you what its points are, I'll try to put a rigid analytic structure on it so it becomes a rigid analytic space, okay? And so the language, I'm just going to introduce some language that it has a bit of a funny feeling to it, but I find it handy to think about. I want to think about eigenpackets, or Hecke eigenpackets in the end, but eigenpackets. So always K will be some finite extension of QP. Lambda will be a Noetherian K algebra. You might think of it as being like the Iwasawa algebra tensored with K, but in fact it will usually be the affinoid algebra of some affinoid subspace of the weight space. Okay, so lambda will usually be something like this, where omega is contained in the weight space that we described yesterday. And then there'll be some ring R. R is a commutative lambda algebra. Okay, now notice that's not much of anything. I didn't say that R is Noetherian or anything. It's just commutative. And so you should think of it as being R is lambda adjoin all the Hecke operators sort of freely as a polynomial algebra with infinitely many variables, one for each n. Okay? So, okay. So then, definition. An eigenpacket, having fixed this data, an eigenpacket is a pair. Phi, I'll call it phi and r phi, where phi, or sorry, r phi, I guess, is a K algebra. And phi is just a map, a homomorphism from R to R phi. Okay, but I want that homomorphism to be surjective. So the surjective ring or K algebra homomorphism to R phi. And I call the weight, think of the weight of such a thing as being the kernel of phi. So in the applications, that will mark a point in the weight space. Okay, and then just to be even more silly, so a morphism, I want to sort of think of this as a category, the category of eigenpackets. So a morphism from one packet to another one is just a homomorphism F from R phi to R psi, making the obvious diagram commute. Okay, and the thing to notice is that because of the requirement that the map phi and the map psi be surjective, if there is a morphism from phi to psi, there's one only. Okay. Okay. Okay, so now if H is an R module, so in practice H will be some cohomology space and R will be the Hecke algebra, and so the Hecke algebra acts on H. Then we let RH be the image of the obvious homomorphism to end lambda of H. Okay, and phi sub H is that map. So that's, that if you like, is the eigenpacket associated to H. Okay, notice that there are no eigenvectors anywhere. Eigenpackets don't have eigenvectors. Okay, not in general. Okay, so anyway, so the definition then, oh, by the way, I'll say that we say that if phi is some eigenpacket, then we say phi occurs in H if there's a homomorphism, if there's a morphism from phi H to phi. Okay, so it's just kind of silly stuff, but it's handy to think this way. Okay, let me just state one thing that is of interest, and that is that the proposition. These are easy things to prove, but there is a little more content to them than you might see at first. Suppose H is a finitely generated R module. And I is contained in RH, some ideal. So let psi be any eigenpacket. But I'm going to assume, I have to assume that psi is reduced. By the way, the adjective reduced refers to the ring that takes the values of psi. So assume that the ring R psi is reduced, has no nilpotent elements. Then psi occurs in H if and only if, psi occurs in H modulo IH if and only if two things are true. Psi occurs in H, and two, psi occurs, psi of the ideal I is 0. And none of this is very surprising, except that I should point out that it's really important that psi is reduced. If the statement is not true if psi is not reduced. And the other thing that's really important is that H must be finitely generated. The proof definitely makes use of the finite generation. Okay? Okay. So now for the points of the eigenvariety. So now I remind you of our situation. We have the weight space. I'm thinking of a point K in the weight space. And you'll remember that for such a thing, I have distributions of weight K. Or I can take, if K happens to be in some aphenoid contained in the weight space, then I can sort of spread that out to distributions over that aphanoid. And I can do things like, I can make a D, sort of over the entire weight space. So we sort of have this picture. And what we're going to do then, the definition is, let C be a k-valued eigenpacket. Then, well, we say, I'm sorry, so let me just describe C of K. Let me define C of K. K was our field. So I'm trying to describe the set of points. That's what I'm really trying to do. C of K is the set of eigenpackets k-valued such that C occurs in the compactly supported cohomology of dk where K is the weight of C. So remember that C is also, it includes a morphism from lambda to K, and that map from lambda to K determines a point in the weight space. And when I say K is the weight of C, that's what I mean. Okay. And so it's like, the idea is that you take for all Ks, for all points K, you form this space. It's an infinite dimensional space. I just point out that H1 compact support dk is an infinite dimensional vector space over the field K. And so we're letting Hecke act on that. And we're then looking at eigenpackets that occur in that infinite dimensional space. Okay, and then we move the point K around, and as K moves around, we get lots and lots of eigenpackets, and those are the points. The eigenpackets that occur in those things are the points of the eigencurve. Okay? But I just remark, and it's an important remark, is that this thing is infinite dimensional. Now, if you have an operator, a linear operator acting on an infinite dimensional vector space, there's no guarantee that there are any eigenvectors at all. Okay? And so why are there eigenvectors? And so, well, the reason is because we have the U operator. We have the U operator, UP, is in the Hecke algebra. Just I'm thinking of this as being the Hecke algebra. And the UP operator is an example of a completely continuous map, H1 compact support, D sub K, mapping to itself, is completely continuous. Now that does require some remarks. The space of distributions itself, the D sub K, is an example of a Frechet space. It's a projective limit of Banach spaces. And so there's a notion of a completely continuous operator on a Banach space, namely it should be the uniform limit of operators of finite rank. And that extends naturally to a notion of completely continuous operators on a Frechet space, namely it should be some sort of limit of finite rank operators. And then I need to remark that when you take the compactly supported cohomology of D sub K, you again get a Frechet space. That's not completely obvious. In this case, you can see it rather clearly, because you remember the compactly supported cohomology is just modular symbols. And so these are functions from divisors of degree 0 on P1 of Q to the space D sub K. And so you can endow that, if D sub K were a Banach space, you would just endow that with the Banach space structure by taking the sup norm of the values of that modular symbol. and then taking the projective limit, this thing becomes, again, a Fouché space, and so it makes sense to talk about complete continuity. Now, the point about complete continuity is that in that case, that we can define a Fredholm determinant, or a Fredholm characteristic power series. I'll call it Fred of UP on H, and I'm going to start writing this simply as HK. So this is, by definition, it's the determinant of the identity minus UP times T acting on that space. Okay, and the fact that this thing is a limit of finite rank operators means that this determinant you can make sense out of it. You can write down, it becomes some power series. This is well defined. I call it P sub K of T. P sub K of T is a power series with coefficients in K, and I'm using curly brackets around the T just to remind you that in fact these guys are entire. So they converge everywhere. The Fredholm, a characteristic Fredholm series is always a series that converges everywhere. Okay, and moreover, this thing, because of the way we formed it, it'll have a constant term. The constant term will be 1. It's called a Fredholm series. A Fredholm series is just a series whose constant term is 1. And so, in fact, this thing factors as a product of this type. Alpha n, say, of K, T, the product over all n. Where the alpha n's, each alpha n is an eigenvector, in fact, or an eigenvalue of UP. Okay, and because of the fact that the power series is entire, it also follows that the alpha n's tend to 0. Okay, and so the Fredholm series, then the Fredholm theory gives us a bunch of eigenvectors, one for each n, for the U operator. The other Hecke operators commute with the U operator. The other Hecke operators commute, and so they'll preserve those finite dimensional spaces. For each eigenvalue of U, there'll only be finitely many with that eigenvalue. That'll cut out some subspace, finite dimensional. The other Hecke operators then act on that, and you can diagonalize using normal linear algebra. Okay, and so that gives you lots and lots of points. So there are lots of points, and those are the ones that we have to put together into some sort of a variety. Okay. Okay. Okay, now, to describe the structure of these things, what we need to do is to think about this characteristic series. And in fact, you can make the characteristic series for any aphanoid omega 0, say, in the weight space. You can form a characteristic series. This is all due to Coleman, Robert Coleman. It's the determinant of 1 minus TUP on H omega 0, where H omega 0 is the compactly supported cohomology of D omega 0. So we're sort of spreading out the characteristic Fredholm series over an aphanoid. Now, because this is defined in terms of the U operator, and because the U operator is defined over ZP, it has norm 1, norm less than or equal to 1. The coefficients of this thing, I should say, so P omega 0 will be some series it'll be 1 plus some sum, n equals 1 to infinity, a n t to the n, where the a n's, I should say this lives in a of omega 0. Okay, so the a n's are affinoid functions on the affinoid space omega 0. So now you might wonder, if you're thinking about this factorization over here, what we're doing is we're spreading the k's out into a neighborhood. But when you do that, you lose the factorization. This beautiful factorization that we have doesn't persist as you get bigger. I should say that all of these guys, I should emphasize this, that they all have, the upper 0 means that they all have norm less than or equal to 1. All the coefficients have norm less than or equal to 1. And I should say also that as you let the omega 0 grow, so there are things like this. If omega 0 is contained in omega 1, you've got 2 affinoids. Then when you take the characteristic Fredholm series over omega 1 and restrict its coefficients to omega 0, you get p sub omega 0. Okay, so this is a beautiful thing. So the coefficients themselves can be extended to functions all the way over the entire weight space. And they happen to have absolute value less than or equal to 1 everywhere. And so in particular, those coefficients are elements of the Iwasawa algebra. Okay, so this all implies that the ANs actually live in the usual Iwasawa algebra, ZP cross in some sense. Okay. Okay. Now, okay. Now, so now suppose this doesn't happen all the time, but suppose that the characteristic Fredholm series p sub omega 0 can be factored as a product q times some f, where q is a Fredholm polynomial and f is a Fredholm series. Both, of course, are going to be entire. And also that f and q as series are relatively prime. Okay, when I say they're relatively prime, what I mean is that the ideal that they generate in A of omega 0 bracket, in the ring of entire power series, contains 1. It generates 1. Okay. Then Coleman gives us a decomposition, H omega 0 equal to H, you call it Q, direct sum H prime, where HQ is, they're both, there's a decomposition into a sum of HQ and H prime are free A of omega 0 modules, or the HQ is free as an A of a 0 module. When I say free, I'll say O-nable, which in the finite case means free. Then, okay, and HQ is as rank over A of omega 0 equal to the degree of Q. Okay, and so what happens here then is that this, and this, there are two conditions. One is that the second condition is that if you take that they're preserved by H, Q, and H prime are invariant for the UPs, and the Fredholm series of HQ times the Fredholm series of H prime is equal to the Fredholm series of H, the whole thing, which is P. Okay, so what's happening here is that you're getting then a decomposition of the cohomology that reflects the factorization of the characteristic Fredholm series. Okay, now what happens now is that the HQ is now finitely generated. Just let me call this this is my lambda now, is finitely generated as a lambda module. And so what that means is that the sets of eigenvectors, sort of eigenpackets, so the conclusion, let me just write it down. So now let's define, I'll call it R of Q. This is the image of Hecke in HQ, in the endomorphisms of HQ. Now, HQ is a finitely generated lambda module, where lambda is an affinoid algebra. And so the image of this then will be a finite over lambda, and will be commutative algebra over lambda. And so in particular, this is an affinoid algebra. And because it's the image of Hecke, we get an eigenpacket from Hecke to R of Q. And then you can see then that the Hecke eigenpackets that occur in the R of Q, so let me let X of Q be the affinoid associated to the affinoid algebra R of Q. And so the X of Q then, if you think about what its maximal ideal spectrum is, a point on X of Q is a homomorphism from R of Q to K, or a K point anyway on X of Q is such a thing. And so by composing that with the R, you will get an eigenpacket. You'll get some sort of an eigenpacket, a K-valued eigenpacket, a Hecke eigenpacket that occurs as a point on this thing. Okay, and so in fact, by the theorem I wrote down before, that an eigenpacket, when you reduce, there's something that I have to say here, and that, let me just say it. The last thing that one has to notice really is that so notice the final fact is that if for each for all K in omega 0, so the Q was a factorization over omega 0, HQ tensor dA of omega 0 over lambda with K, with respect to that point, at that point K, is the compactly supported cohomology with values in that particular thing on which Hecke acts via Q. Let me say Q equals 0. It's actually Q star equals 0, but there's a particular set of eigenpackets that occur there. And so in particular, this is just HQ modulo the maximal ideal associated to the point K. And so the statement that I wrote down at the beginning, that eigenpackets that occur in this quotient are the same as eigenpackets that occur here, or k-valued eigenpackets that occur in HK, is just the statement that every point in X of Q really does occur as an eigenpacket in the H1 DK. Okay, that's not, that statement, it sounds like I'm saying something tautological, but I'm not. There's some statement that one needs to make. Okay, so we're using the fact that this thing is of finite rank in order to say that. In any case, so that gives us then these aphanoid pieces, and their points are in one-to-one correspondence, so we can view X of Q as being contained, or the K points anyway, as being contained in what I call the K points of C of K. And this now is an aphanoid. And so that gives us a cover. You just have to check that that actually gives us an admissible cover of this particular set. You have to show how to glue things together, but it's not too hard to do. And I think I'm going to stop right there. Okay?